Hello guys, welcome to my channel. Today we will be solving a classical DC problem sliding window maximum. We will be having a look at brute force solution and the super efficient optimized solution for this problem. So first understand what is the problem. The problem is very simple. The problem is very straightforward. You are given an array of numbers and a window size. Let's call it k. Imagine a window of size k that slides from very beginning of the array to very end. For each position of the window, you need to find the maximum number inside it. Let's take a simple example. Array 1 3 minus 1 minus 3 5 3 6 7. We have given window size of 3. The first window is 1 3 minus 1. The maximum number from this window is 3. The window slides one position to the right. 3 minus 1 minus 3. Again, the maximum is still 3. Next window, minus 1 minus 3, 5. Maximum is 5. And so on until we reach the end of array. Our output should be a list of these maximums: 3, 3, 5, 5, 6, 7. The brute force of us says that we have to use the two for loops. The outer for loop will be responsible for the iterations of the window positions, and the inner loop will iterate through k elements inside that window to find the maximum. The pseudocode for the brute force approach will look like this. Inside the function sliding window maximum, we will be having array and the k, which is the size of window. We created the result array to store the maximum number of each subarray. Outer loop will iterate from the start of the array up to the point where a full window can be formed. The question is that up to which element the full window will form. So the answer is the total length of array minus the size of each window. So from I to length minus k will be iterating. We have to assume that the first window is the maximum. We assign current maximum as first element of the array and then we will do run inner loop. This loop will run from I plus 1 to I plus k minus 1. So for first index it will be running from 1 to 2. That will cover 3 elements first. So this loop will run, and at the end we have to add the maximum to our result, and at the last we have to return the results. So now let's take an example to understand in more detailed manner. So let's use our example array 1 3 minus 1 minus 3 5 3 6 7 and k is equal to 3. For I is equal to 0, window is 1 3 minus 1. The inner loop runs, compares 1 3 and minus 1 and finds maximum is equal to 3. And then it will store result as a 3, and then for I is equal to 1, it will run for and compare 3 minus 1 and minus 3 and will be getting maximum as 3, and then window for I is equal to 2 is minus 1 minus 3 and minus 5, and the inner loop will run to find maximum as a 5, and then this loop will continue at the till end. So discussing time complexity of this brute force solution, for each starting position of the window there are n minus k plus 1 of them, which will be roughly n. We do k work with to find the maximum. This gives us the time complexity of big of n into k. This works, but it is slow. If the array has a million elements and k is 100,000, this approach will be very slow. I hope you have understood the brute force approach of the solution. This loop runs n times in this outer loop, and for each iteration it is running k times. So that's why its time complexity is big O of n into k. So now let's move to the optimized approach of this problem. We will be using the DQ, which having both ends open, we can do much better. The key to optimizing is to avoid recalculating the maximum for each window. We can cleverly use the information from the previous window. The perfect data structure for this is DQ, which is double-ended queue. We can add or remove elements from the both front and end. Here is the logic. We will store indices of the elements in our DQ, not the elements themselves. The DQ will be maintained in decreasing order of values. This means the index at the front of the DQ always contains the largest element in the current window. So now listen these three steps. Clean the front. Before processing the window, look at the index at the front of the DQ. If it is outside the bound of the current window, remove it. So to avoid the out of bound going outside the window, we will be removing the element which are the outside of our window size. And then clean the back. Look at the new element we are adding. While the DQ is not empty and the element at the back of the DQ is smaller than our new element, remove it from the back. Why? Because if the new element is bigger, that smaller element can never be maximum in future window. It's now useless. This means that if the ith element we are trying to add in our DQ is greater the elements which are present in our DQ previously that are smaller than the current element, we have to remove it because they will never be the maximum element for that current window size. And then we have to add the new element. Add the index of the current element to the back of the DQ. Once the window is fully formed, the element at the front of the DQ is 1 or maximum. So let's take a look at the pseudocode. We form the function sliding window max optimize k, and we form the results array to store the result, and then we form the DQ to store indices, and then we iterate from I is equal to 0 to length of array minus 1. Then we check for is our DQ is empty or the element at the front of the DQ is less than the current element index of the array minus the window size. If it is true, then we have to remove the element at the front of our DQ because it is causing out of the window elements to get inside the DQ. Then we have to check for the back elements. Remove smaller elements from the back while DQ is not empty. An array of DQ of back is less than the current element of the array. If this condition is true, we have to remove the elements from the back of the DQ because these elements will never be maximum for our current window size. And then we have to add the current element index into our DQ. If we have a full window means a value of I is greater than or equal to window size minus 1, the front of the DQ is the max for the current window because we are storing the values in the DQ in increasing order. The maximum index of the maximum element will be at the front of the DQ. And then We have to add that element into the result array, and then this process will be continued till the end of the array, and then at last we have to return the results. So let's walk through the example. So as we earlier discussed, the conditions are while dq is not empty and the element at the peak of the dq is less than equal to I minus k, we have to remove the element from the dq and the both conditions respectively. So let's walk through the example. Firstly, for ith element, we have nums 1 as element. First condition and second condition will be false, and then we will push that element's index into the dq, and the dq will look like 0 and the respective element, and therefore then for element is equal to 1, we will be having element 3. We will check second condition. If 1 is less than 3, we have to pop the index 0 in the dq, then the dq will look like 1, and 1 will be at the front of the dq because we popped the 0. And then for I is equal to 2, the element is minus 1, we'll directly push it into the dq, and our dq will look like 1 and 2, where 1 is at the front, and as there this fourth condition become true, we directly push the result into the result array, giving the maximum element as a 3. Then for I is equal to 3, minus 3 is the element where we check both the conditions which become false, and then we push 3 as index into our dq, and then we again get 3 as a maximum element, and then we move for I is equal to 4 when nums of I is equal to 5, and then we check for the out of window condition where we find 1 is less than 1. Then we pop 1 to avoid the out of window condition, and then we move for second condition where the ith element is greater than the previous element of the dq. Then we remove the dq, remove the elements from the dq to store the maximum element in the dq. So we will be having 4 index and the maximum respective maximum element in the dq. So the maximum number from the dq at the front is 5. Next, I is equal to 5. We will checking both A and B conditions which will become false, and then we will be pushing 5 in our dq, and then it will be checking the front element at the dq. So the front element at the dq is 5 again, so we'll be pushing the 5 as a maximum element in that respective window. And then for I is equal to 6, we will be having nums of I same as 6. Then we will be checking the both conditions. First condition is false, but second conditions became true as 6 is greater than 3 and 5 is less than 6. So we pop 5 and 4 from our dq and push 6 into the front of the dq, and then at last to push the element into the result, we push the front of the dq in our array. So for last element as a 7, we check for I is equal to 7. The first condition become false as 6 is less than 4 is not true. We check for the 7 is greater than 6. Then we pop 6 and push 7 in the front of the dq. Then we find that 7 as the maximum element in the front of the DQ. In this way, we found the maximum element in each subarray of size k. So, for this code in Java, we found that this outer loop is running for n times and the inner loop, which is popping the element and the pushing the element in the DQ, is running respectively big of n times, and the total time complexity of the solution will become big of 2n times. That means it is running approximately in big O of n times. That means faster than the brute force solution. So I hope you have understood the solution of this question. If you like this video and understood the solution, please like, share and subscribe this video and follow me for more such content on tech problems. Till then, keep growing and keep exploring.